Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool, and in today's video I'm going to talk to you about pressure drops. Now in our last video on the hydraulic design of borefields, we talked about connections in series and parallel. There we mentioned that the pressure drop is also an important aspect of your hydraulic design, but it's often overlooked in practice. So today I'm going to talk to you about what exactly is the pressure drop, why it is important, how it relates to pump design, to pump energy, and in the next video we will show you how GHEtool Cloud can actually help you designing your system with the pressure drop in mind. Now the pressure drop is typically a difficult or sometimes difficult fluid dynamic parameter where there is quite a lot of information already available online. So in this video I will try to do things more from a loose physics point of view, let's say, where we want to focus more on the insight and the reasoning behind everything. So let's get started. So what exactly is the pressure drop? If we look at the strict scientific definition, we see that the pressure drop is defined as the difference in pressure between 2 points caused by friction. Friction between the fluid and the pipe, between the fluids internally, as well between the different molecules. So if we translate this to a more easy to use language, let's say, you can say that the pressure drop is the effort we need in order to pump our fluid through the system. So this of course relates to the flow rate. If we want to have more fluid passing through a borefield, we need more effort because we need to overcome this pressure drop, this higher pressure drop. If we decrease our pipe diameter, we will have more friction with the surface. We will have a higher fluid velocity. This will also increase the pressure drop and the effort we need to take in order to pump this fluid through our system. When we have a higher viscosity, the same thing happens. Just imagine that you fill your borefield with honey instead of water. You will need way more power, way more effort in order to pump this whole honey system or honey fluid through your borefield. But there are other aspects that relate to this pressure drop. Imagine that you have different routing of the pipe. So you can have your horizontal interconnections beautifully straight, all parallel, or you can have them with twists and bends all over the place. The situation where there are quite a lot of bends, quite a lot of right angles, will have a higher pressure drop and the pump will have to work harder in order to get the fluid through that system. Systems with a lot of T connections, with a lot of interconnections, also typically tend to have a higher pressure drop and hence need more pump power in order to get the fluid flowing through that borefield. So when we talk about the pressure drop, you can see that we tend to have this distinction between either local losses, also called minor losses, which you can localize in a system. These are typically the bends, the T connections, but also valves are calculated as being local losses. And typically local losses are defined by a certain factor to take into account the way they cause pressure drop, which you will see in the next slide. So as you can see, if we have, for example, a smooth 90 degrees bend, we have, in case it's a threaded connection, we have 0.9 as a factor. When we have just a right angle, we have 1.1. So this is a worse situation than the first one. So this is everything related to local losses. There are tables you can find just like this one with all the different factors there. On the other hand, you have what's called friction losses, also called major losses. And these occur in the pipes themselves. And these depend on the length of your pipe and the diameter and cannot specifically be localized to some particular part in your system. So let's now take a closer look at how both losses are calculated and how you can come up with the total pressure drop. So the local losses are defined or can be calculated as follows. So your pressure drop is equal to the sum of all these local pressure drop factors multiplied by rho V squared over 2. So where rho is the fluid density and V is the fluid velocity squared. So this is the formula how you can take into account your local losses. On the other hand, you have what's called friction losses. And this one is slightly more complicated. In order to take into account the friction losses or the major losses, there is something called the Darcy-Weisbach equation, which looks like this. So you have again the pressure drop, but now for the friction losses, which is equal to a certain friction factor multiplied by the length divided by the pipe diameter multiplied again by the fluid density multiplied with the velocity squared over 2. So here you can see that if you have a pipe that's twice as long, the pressure drop will also be twice as big. And if you divide the pipe diameter by a factor of 2, the pressure drop will increase by a factor of 2. But an important factor in this equation is of course this fluid friction factor. This fluid friction factor can be found by taking a look at what's called the Moody diagram. Now this is a complicated graph that's rather famous in the domain of fluid dynamics. So let's take a closer look at it. First of all, I want to say that this graph is in a log-log scale. So both axes are in a logarithmic scale. And on the x-axis you have the Reynolds number. Now if you have not watched our video on the Reynolds number yet, please go ahead and do so. But to summarize, the Reynolds number is a dimensionless number that tells you something about the state of the fluid. Is the fluid laminar or is it turbulent? Now when it's laminar, all the fluid particles move in, let's say, parallel trajectories next to each other. When it's a turbulent flow, they fall over each other, they tumble across each other, and there is quite a lot of, yes indeed, turbulence there, as you can see in the figure on the right. Now what can you see on this Moody diagram? There are quite a lot of lines on it, but it's basically divided into two regions. You have, for the lower Reynolds number, you have the laminar flow, and for the higher Reynolds number, you have multiple lines for the turbulent flow. Now this is indeed a strange thing to notice, that when you have a turbulent flow, there are more lines, more curves than in the laminar flow. Now let's take a look at these different curves. All the lines you can see here on the graph in the turbulence zone have different relative roughness levels. So what do we mean by that? Well, if you take a look at your pipe and you would zoom in on the surface boundary, you would see that it's never really flat. There is always a kind of roughness of surface irregularities. Now, of course, when we work with smooth pipes in our typical geothermal systems, these are very, very smooth because it's PE. But if we take, for example, a closer look at steel walls or even concrete pipes, these typically have a very high, or very high, it's all relative of course, but a higher relative roughness factor. Just feel a concrete sewage system, for example, you will feel the granularity of the surface, whereas with a smooth pipe, you typically don't feel anything at all. So in our geothermal applications, we tend to have systems with 10 to the minus 5 of this relative roughness, so really close to the smooth system. But for reasons too complicated to explain this video, in our laminar case we only have one equation for a fluid friction factor, which is 64 divided by the Reynolds number. And then we have a sudden jump to our turbulent regime. And there you see that the friction factor decreases only slightly with the Reynolds number, and after a certain amount of time it stays constant. Now typically in your geothermal systems you do not reach this point. We typically have systems that are around this turbulent laminar zone, this transition zone. So this is typically where we work. And important to notice here that if we move from the laminar flow to the turbulent flow in the transition zone, that we have typically a way higher fluid friction factor. So now that we know this, we know that the total pressure drop can actually be defined by summing both the major pressure losses, the friction losses, and the local pressure losses. And as you can see, this is all quadratically proportional to the fluid velocity. So if we increase the flow rate through our system, we typically tend to have a quadratic expression for the pressure drop. It's not 100% quadratic because the fluid friction factor also changes, but typically this is the type of figure you have. Now this is important to understand, because when you're designing your geothermal system you typically enter a mass flow rate, you enter a flow rate for your system. But it's important that your pump can also deliver the needed pressure in order to be able to achieve this mass flow rate, to overcome this larger pressure drop. And that's why pump design is so important. Now for smaller projects, this pump is included in the heat pump itself. So you typically do not design a primary pump, but it's there important to check whether or not your pump can actually handle the larger pressure drop. And I've taken an example from a heat pump from Nibe here, the S1156 for 8 kilowatts. And this is directly from their technical documents. So what you can see here are the red lines. These are the pump characteristics for a 40, 60, 80 and 100% power. And also the blue lines for their electricity consumption. Now this is not important for us. What is important are the red lines, and especially this larger red line. So what you can see on this line, or what this line means, are all the different working points which are feasible with this heat pump. So let's say if we want a flow rate of 0.5 liters per second through our heat pump, we know that this heat pump or the primary pump can deliver it with a pressure drop of 20 kilopascal. If we want to have a lower flow rate, for example, of 0.2, we can have 60 kilopascal. So every point in the region under this red line of 100% is a feasible working point. It can be delivered by your system. So imagine that you design your borefield to work for, let's say, with 0.4 liters per second, and you calculate that you need to have 32 kilopascals to do it. Then this is feasible with this heat pump, and your system will actually work in that designed point. But imagine you have designed your system to work with 0.36 liters per second, and you require 60 kilopascal of pressure drop. Then your pump will not be able to deliver this. So the efficiency which you calculated using GHEtool, for example, using a particular mass flow rate, cannot be achieved by this pump. So you will have to either redesign your borefield using a feasible working point, or you need to select another primary circulation pump that can actually deliver this working point. Now, another thing next to the design of the right pump is the pump energy. And I can show you this in this simple table where you have 3 different designs, a single U-tube with a DN32, a DN40, and we have also a double U-tube with a DN32. We have the same flow rate through the borehole of 0.3 liters per second. You can see here the Reynolds number, but also the pressure drop and the yearly electricity consumption. So as you can see with the single DN32, we have a Reynolds number that's in the transition zone. So when it comes to the pressure drop, it's already turbulent. There is not such thing as a stringent pressure drop that's taken into account. So what you can see here is that it's a rather big pressure drop of 83.97 kilopascals, which leads to a yearly electricity consumption of around 38 kilowatt hours per year. Now, in case you have a single DN40, you will also have the same mass flow rate. We have now a laminar Reynolds number, and you see that the pressure drop is immediately significantly lower, and so is your electricity consumption over the years. And just as a reference, if we have a double U, DN32, we have an even lower Reynolds number because we now have a bigger surface area, but the pressure drop is slightly higher than the single U-tube, although our Reynolds number is lower. And this is due to the fact that it's not only the fluid velocity that's taken into account, but also the pipe diameter in our friction parameters. So just to show that designing your system with a turbulent flow or a transient flow will lead to very high pump energy requirements, leading to an overall worse performance of your system. So this was basically the theoretical foundation I wanted to give you related to the pressure drop. Now in the next video, in 2 weeks, we will show you how you can design a particular bore field, taking this pressure drop into account. We will work out 1 or 2 examples together so you can get started with calculating the pressure drop for yourself and check whether or not your heat pump can actually deliver the pressure drop you need in order to get the performance you designed your system for. So I hope to see you in that next video. Take care. Bye.